Right now, without feeling a thing, you are moving. Not just spinning with the Earth, not just circling the sun, but drifting, along with the entire Milky Way, at hundreds of kilometers per second, towards something astronomers can barely see. And we are not moving alone. Roughly 100,000 galaxies are sliding through the dark in the same vast current, all of them caught in the same immense gravitational basin. Its name is Laniakea, and until 12 years ago, we didn't even know it existed. We thought our galaxy was a lone island. Instead, it turns out we live on the gentle slope of a cosmic valley, 500 million light years across, flowing toward a destination we still can't fully explain. So where exactly are we falling, and why? Before we drift any deeper into this, if you find this kind of cosmic exploration fascinating, a quick like or subscribe really helps this channel keep growing. It's a small thing for you, but it means a lot to me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Picture yourself standing perfectly still. You're not walking, not driving, not moving a muscle, and yet in this very moment, you're being carried through space at a speed that's almost impossible to put into words. The Earth beneath you is spinning at over 1,000 kilometers per hour. That spinning Earth is racing around the Sun at about 30 kilometers per second. The Sun itself is sweeping around the center of our galaxy at roughly 230 kilometers per second. And the entire Milky Way, with all of its hundreds of billions of stars, is drifting through the cosmos at something like 600 kilometers per second, relative to the ancient glow left over from the birth of the universe. You feel none of it. There is no wind, no rumble, no sense of speed at all. But you are falling. We are all falling. And the strangest part is where we are falling toward. And that figure I gave you, the 600 kilometers per second at which our whole galaxy drifts, is not a guess. We can measure it directly, and the way we do is beautiful. Filling all of space is a faint afterglow left over from the birth of the universe, a whisper of radiation called the cosmic microwave background, almost perfectly even in every direction. Almost. Because we are moving through it, that afterglow looks very slightly warmer in the direction we are heading, and very slightly cooler in the direction we are leaving behind. Exactly the way running through still air makes the air feel like a breeze on your face and a calm at your back. By measuring that tiny warm-cool lopsidedness across the sky, astronomers can read off the speed and direction of our motion against the backdrop of the entire universe. And what it tells us is that our whole neighborhood is barreling along at about 600 kilometers per second toward a particular patch of sky. That measurement, more than any other, is what first told us something out there was pulling us. It was the original clue, the first hint that we were caught in a current at all. Because here's the thing that took astronomers decades to even begin to understand. The Milky Way is not drifting through space on some lonely, random path of its own. It is moving as part of something far larger than itself. Our galaxy is one tiny passenger inside an immense, flowing current of galaxies, a slow river of matter so vast that the human mind simply has no shelf to put it on. Roughly 100,000 galaxies are caught up in this same current, all of them sliding through the darkness, all of them gently sloping in the same general direction, drawn together by the combined pull of everything around them. And this colossal region, This enormous basin of flowing galaxies that contains our Milky Way and 100,000 others has a name. It is called Laniakea. That name comes from the Hawaiian language, and it was chosen with real care. It means, roughly, immeasurable heaven, or immense heaven. And honestly, no name could fit better, because once you understand what this thing actually is, immeasurable feels like an understatement. It is worth pausing on that name and where it came from, because the story is lovely and it tells you something about how new this knowledge really is. The discovery was announced in the year 2014, which in the grand history of astronomy is essentially yesterday. The team that mapped it was led by the astronomer Brent Tully, working with an international group of colleagues including Hélène Courtois and Daniel Pomerede, piecing together the motions of thousands of galaxies. When it came time to name the immense structure they'd found, they turned to a Hawaiian language professor named Nawa Napoleon, who suggested Laniakea. The word joins two Hawaiian roots, one meaning heaven or sky, the other meaning spacious or immeasurable. And the name was chosen in part to honor the Polynesian navigators, the wayfinders who crossed the vast emptiness of the Pacific Ocean for thousands of years, guided only by the stars, reading the sky to find their way across an ocean so wide it might as well have been space. There is something perfect in that. A structure mapped by reading the motion of the heavens, named in honor of a people who learned to read the heavens to navigate an ocean. The wayfinders found their islands by the stars. The astronomers found our cosmic island by the galaxies. And both, in their way, were charting a home in an immensity too large to see all at once. Laniakea stretches across about 520 million light years of space. Let me try to make that number mean something, because thrown out like that, it's just a sound. Remember that light is the fastest thing in the universe, traveling at about 300,000 kilometers every single second. In 1 year, light covers roughly 9.5 trillion kilometers. That distance is a single light year. Now multiply that by 520 million. To cross Laniakea from one edge to the other, a beam of light, moving at the ultimate speed limit of the cosmos, would need 520 million years. When a ray of light leaves one side of this structure, complex life on Earth has not yet crawled out of the oceans. By the time that ray reaches the far side, fish have evolved, crawled onto land, become dinosaurs, gone extinct, and been replaced by mammals, and human beings have built cities and telescopes and finally looked up to measure the very thing that light has been crossing the entire time. That is the scale of the place we live in. And our galaxy, the Milky Way, which is itself about 100,000 light years across and contains somewhere between 100 billion and 400 billion stars, is just one speck inside it. If you imagine the entire Laniakea structure shrunk down to the size of a large city, the Milky Way would be smaller than a single grain of sand lying somewhere out near the suburbs. One grain of sand among 100,000 others, scattered across the whole sprawling metropolis, and every one of those grains is itself a galaxy, a city of billions of stars, many of them almost certainly circled by planets, and some of those planets perhaps circled by oceans and atmospheres, and who knows what else. So how much matter does it take to make a structure like this? The total mass of Laniakea is estimated at something on the order of 100,000 trillion times the mass of our sun. Try to sit with that for a second. Our sun is already so massive that it contains about 99.86% of all the mass in our entire solar system. Every planet, every moon, every asteroid and comet combined makes up less than 1% of the rest. The sun could swallow over 1 million Earths. And we're talking about a region of space holding the equivalent of 100,000 trillion of those suns. Of course, most of that mass is not actually in the stars at all. The overwhelming majority of it is dark matter. That invisible, mysterious substance that we cannot see directly, but whose gravity shapes everything. The stars and galaxies we can actually observe are like the foam on top of a deep, dark ocean. They ride on top of a vastly greater hidden mass, and it is the gravity of all of it together that organizes this immense flowing region. Now, here is where this story takes a turn that I think is genuinely beautiful, and it's the heart of what makes Laniakea such a profound discovery. For most of the history of astronomy, when scientists wanted to map the large-scale structure of the universe, they did the obvious thing. They counted galaxies. They looked out into the sky, found where galaxies were clumped together most thickly, and drew their maps based on density. Where there were lots of galaxies packed close, that was a cluster. Where clusters gathered near other clusters, that was a supercluster. And where there were vast stretches of near emptiness, those were the voids. It was, in a sense, a map made by counting lights in the dark. You looked for where the lights were brightest and most crowded, and you called that a structure. That approach makes intuitive sense, and it gave us real knowledge. But it has a deep limitation, and the limitation is this. Just counting where galaxies appear to pile up does not tell you what those galaxies are actually doing. It does not tell you which way they are moving, or what they are bound to, or where they truly belong. Imagine trying to understand a country by taking a single photograph from high above and just marking where the cities are densest. You would learn something, sure, but you would have no idea about the roads, the rivers, the direction people travel, where the borders really lie, or which towns share a common destiny. A photograph of density is a frozen snapshot. It is missing the most important ingredient of all, which is motion. And this is exactly the leap that defined Laniakea. Tully and his colleagues, the same team, did not draw its boundaries by counting where galaxies are thickest. They drew its boundaries by tracing how galaxies move. They asked a completely different and far deeper question. Not where are the galaxies, but where are the galaxies flowing? And when you map the universe that way, by motion instead of by brightness, something extraordinary happens. A hidden landscape appears that was completely invisible on the old density maps. Vast currents of galaxies reveal themselves, all streaming together, all sliding down the same great gravitational slopes. And the place where all those flows converge, the entire basin that shares one common direction of fall, that is Laniakea. It was the first time anyone had defined a supercluster not as a pile of galaxies, but as a region of shared movement, as a watershed of cosmic flow. I want to make sure that distinction really lands, because it changes everything about how you should picture our place in the cosmos. Think about how we define a river basin or a watershed here on Earth. You do not define a watershed by where the most water happens to be sitting at any given moment. You do not just point at the biggest lake and say, that is the watershed. Instead, you define it by drainage, by flow. Every drop of rain that falls within a certain region will eventually trickle downhill and drain into the same river, the same sea. And there is an invisible dividing line, a ridge in the landscape, where on one side every drop flows toward one ocean, and on the other side every drop flows toward a different one. That dividing line might run right across an unremarkable patch of ground where there's no obvious landmark at all. You could be standing with 1 foot in one watershed and 1 foot in another and never know it, because the boundary is not about what's sitting there. It's about which way things flow. Laniakea is defined in exactly that way, but on a scale that dwarfs anything on Earth. It is a cosmic watershed. Within its boundaries, all the galaxies, despite their tangled and complicated individual paths, are on average flowing toward the same deep region of gravitational pull. They are draining, in a sense, toward the same valley floor. And somewhere out there in the dark is the dividing line, the cosmic ridge, beyond which galaxies stop flowing toward our basin and instead begin flowing toward a different one entirely. Galaxies just on our side of that line are part of our home. Galaxies just on the other side belong to a neighboring structure, sliding away from us toward their own separate destination. That boundary is not marked by any wall, any cluster, any visible thing at all. It is marked purely by the direction of motion. And that is what makes this kind of map so radically different from the old way of counting lights. This is the single most important idea to hold on to, so let me say it plainly. There are two completely different ways to define a structure in space. One is a density map, which asks where galaxies are crowded together. The other is a velocity flow map, which asks where galaxies are moving toward. These can give you very different pictures. The old density-based superclusters were real in their own way, but they were a bit like outlining a city by where the streetlights cluster. The flow-based definition of Laniakea is something deeper. It outlines our home by where everything is gravitationally falling. It is the difference between a still photograph and a map of the currents in the sea. And when astronomers finally made that map of the currents, they discovered that we live in a basin several times bigger across than the supercluster anyone had assigned us to before, and vastly larger in volume. They had to expand our cosmic address by an enormous factor because the flow showed that structures we had thought were separate were all part of one connected drainage system, all sloping the same way. Now, you might be wondering, how on earth do you measure the motion of a galaxy that is tens or hundreds of millions of light years away? How do you possibly know which way some distant smudge of light is drifting, when even at the speed of light, its journey to us takes longer than the age of complex life? That is a fair question, and it is the engine that drives this entire discovery. The full answer is something I want to walk through carefully, because it is one of the cleverest pieces of detective work in all of modern science, and it depends on separating two completely different kinds of motion that get mixed together in everything we observe. But before we get there, I want you to simply absorb the picture itself, because the picture alone is staggering. We are not at the center of anything. That is the first thing this map teaches us, and it is a lesson humanity has had to learn over and over again, each time more humbling than the last. Long ago, people believed the Earth sat at the center of all creation, with the sun and stars wheeling around us. Then we learned the Earth orbits the sun. Then we learned the sun is just one ordinary star among hundreds of billions, sitting not at the heart of the galaxy but far out in a quiet spiral arm, about 26,000 light years from the galactic center. Then we learned that our galaxy is just one among a small cluster of galaxies, and that cluster just one among many in a supercluster. And now, with the mapping of Laniakea, we learn the deepest version of this lesson yet. We do not sit at the center of our supercluster. We do not sit anywhere near the bottom of the basin where everything is flowing. Instead, our Milky Way lives way out on the distant outskirts, high up on the gentle sloping rim of this enormous valley, far from the main concentration of the flow. We are like a single house perched on the upper edge of a vast watershed, near the very ridge that separates our basin from the next one over. We are not at the heart of Laniakea. We are clinging to its frontier. And the structure itself, this immense basin, is nothing like the neat, tidy sphere you might imagine when you hear the word supercluster. It is not a ball. It is not a smooth blob. It is a wildly irregular, sprawling, branching shape, full of dense knots where galaxies pile up into great clusters, threaded through with long stringy filaments of galaxies stretching across tens of millions of light years, punctuated by enormous empty voids where almost nothing exists at all. If you could somehow see it whole, lit up and laid out before you, it might remind you of a great branching root system, or a network of rivers and tributaries all draining toward a single delta, or the delicate, tangled threads of a spider's web stretched across an impossible distance. There is a long, dominant region where the flow is strongest, almost like the main trunk of the whole structure, and our galaxy sits far out along one of its lesser branches. The shape is messy because gravity is messy. It pulls things into clumps and strands and sheets, never into perfect geometry. And tracing the true outline of that messy, flowing shape is only possible because astronomers learn to read motion instead of just brightness. There is one more thing I want to be very careful and very honest about, right from the beginning, because it is easy to get the wrong impression. When I tell you that 100,000 galaxies are falling together, it would be natural to picture all of them racing inward like water spiraling down a drain, all of them aimed at one single point in space, where they will eventually pile up. That is not what is happening, and the reality is far more subtle and far more interesting. These galaxies are not all rushing toward one exact spot. Each one is being tugged in many directions at once, pulled by nearby clusters, pulled along filaments, pulled by the great hidden masses of dark matter scattered throughout the region. Their paths are complicated, looping, wandering things. When astronomers say they're flowing together, they mean it in the gentle, average sense of a watershed. On the whole, across the whole vast region, the net drift is in a common direction. But no individual galaxy is on a simple collision course with some cosmic bullseye. Each traces its own winding, looping route, nudged this way and that by everything it passes, even as the whole vast population drifts, on balance, the same way. The flow is real. The shared direction is real. But it is a tendency, an average, a vast and patient drift, not a frantic plunge toward a single drain. And I should also tell you plainly that even the number 100,000 is an approximation. It is not the result of someone counting every single galaxy in the region one by one and arriving at an exact tally. It is an estimate, a best guess based on the volume of the basin and the typical density of galaxies within it. The true number could be somewhat higher or somewhat lower, and it depends in part on exactly where you decide to draw the boundary, which itself is a matter of how you define the flow. The same caution applies to the size and to the mass. These are not precise, final, carved in stone measurements. They are careful scientific estimates, and like all such estimates, they come with real uncertainty, Laniakea is not a sharply edged object you could trace with a pen. It is a vast, fuzzy, flowing region whose boundaries are defined by something as delicate as the direction galaxies happen to be drifting. Holding that uncertainty in mind is not a weakness in the story. It is part of what makes the achievement so impressive. Astronomers managed to find structure, real structure, in something this enormous and this subtle. To place this in one more frame, consider the observable universe itself. The whole sphere of space from which light has had time to reach us since the universe began. This sphere is about 93 billion light years across. Set our basin against it, and Laniakea, for all its half-billion light-year sweep, spans only a small fraction of 1% of that width. If the observable universe were the size of an entire country, Laniakea would be something like a single large city within it. The Milky Way one building somewhere in that city, and the sun a single grain of dust resting on one windowsill of that building. And here is a number to set beside our 100,000 galaxies. The observable universe is thought to contain something like 2 trillion galaxies in total. 2 trillion. Our entire basin, the whole flowing home we have spent so long mapping and naming, accounts for roughly 1 part in 20 million of all the galaxies we could ever see. We are not a large fraction of the cosmos. We are a vanishingly small corner of it that happens to be ours. And one final caution, because it matters and it's easy to misunderstand. As immense as Laniakea is, it is absolutely not the largest structure in the universe. It is not the edge of everything. It is not the biggest thing there is. There are larger structures out there, longer walls and threads of galaxies stretching across even more incomprehensible distances. And there are things pulling on Laniakea itself from beyond its own borders, even greater concentrations of mass tugging our whole basin in their direction. So please do not walk away thinking we have found the ultimate, final, biggest container of all. We have not. What we have found is our home basin, the particular valley in the cosmic landscape that we happen to belong to, the watershed whose currents carry our galaxy along. And that, all by itself, is more than enough to redraw your entire sense of where you live. Because think about what this actually means for you. Standing there, motionless, feeling nothing. The ground under your feet is part of a planet, and that planet is part of a solar system, and that solar system is one of billions in a galaxy, and that galaxy is one of 100,000 in a flowing basin, 500 million light years wide, and all of it, every bit of it, is sliding together through the dark toward the deep, gravitational heart of a structure we have only just learned to see. You are not standing still at all. You are riding a current older than the Earth, wider than the imagination, a current that was set in motion by the gravity of matter that gathered before the sun was ever born. And until about a decade ago, no human being even knew this current existed. We thought we were islands. We thought each galaxy drifted more or less on its own. And then a handful of scientists figured out how to read the motion of the heavens. And the whole hidden landscape of our cosmic home revealed itself, like the lights of a vast valley suddenly coming on in the dark. The question that should be burning in your mind right now is the same one that drove this entire discovery. How? How do you possibly measure which way a galaxy hundreds of millions of light years away is drifting? How do you tell the difference between a galaxy moving because the whole universe is expanding and a galaxy moving because something is pulling it? How do you take thousands of those distant ghostly motions and weave them into a map of an invisible gravitational landscape you can never touch or visit or see directly. That is the real heart of this story. So let me show you how it was actually done. Because the method astronomers use to uncover Laniakea is, in many ways, even more astonishing than the basin itself. It required them to separate two motions tangled together in every single thing we observe in the sky, to subtract the expansion of the entire universe from the gentle drift of gravity, and to reconstruct, from nothing but the directions galaxies are sliding, the shape of a hidden valley spanning 500 million light years. And once you understand how they did it, you will never look at a smudge of distant light the same way again. So let's return to that burning question. How do you possibly measure which way a galaxy hundreds of millions of light years away is drifting through space? You cannot fly out there and watch it. You cannot plant a flag and clock its speed. All you have is the faint light it sends across the cosmos, light that left it millions of years ago. And yet, hidden inside that light, encoded in it like a message written in a language we have only recently learned to read, is the secret of its motion. The trick is knowing how to decode it, and even more importantly, knowing how to separate two completely different kinds of motion that are tangled together in everything we see. Because here is the deep problem that astronomers had to solve before they could ever draw the boundaries of Laniakea. Every galaxy in the sky is moving for two entirely separate reasons at the same time, and unless you can pull those two reasons apart, you can learn almost nothing about gravity at all. Let me start with the first kind of motion, the one that dominates everything and that you have probably heard of before. The universe is expanding. This is one of the most important discoveries in the history of science, and it goes back to the astronomer Edwin Hubble, who in the late 1920s made an observation that shook the foundations of how we understand reality. He found that almost every distant galaxy is moving away from us. And not only that, he found that the farther away a galaxy is, the faster it is receding. A galaxy twice as far away moves away twice as fast. A galaxy 10 times as far away moves away 10 times as fast. This relationship, this clean and simple proportion between distance and speed, is one of the most profound patterns in all of nature. And it tells us something staggering. The galaxies are not flying apart through space like shrapnel from an explosion. Instead, space itself is expanding, stretching, growing, and carrying the galaxies along with it. The image people often use, and it is a good one, is raisins in a loaf of bread dough as it rises in the oven. Imagine you are a single raisin somewhere inside that dough. As the dough expands, every other raisin moves away from you. The raisins close to you drift away slowly, because there is only a little dough between you and them, and that little bit of dough is only expanding a little. But the raisins far across the loaf race away from you quickly, because there is a great deal of dough between you and them, and all of that dough is expanding at once, adding up to a much greater speed. You are not special. A raisin on the other side of the loaf sees exactly the same thing, with every other raisin fleeing from it. There is no center. There is no edge from which everything is flying. The expansion happens everywhere, all at once, and it carries everything along. That is what the universe is doing. The galaxies are the raisins, space is the dough, and the whole thing has been swelling for nearly 14 billion years. But how could anyone possibly know that a galaxy is moving away from us in the first place? You cannot watch it recede in real time. You cannot clock it against a roadside marker. The answer lies in one of the most useful tricks in all of astronomy, a trick hidden in the colours of light itself. Light travels as a wave, and the colour of light depends on the length of that wave. Shorter waves look bluer, longer waves look redder. Now, when an object that is giving off light moves away from you, the waves it emits get stretched out, lengthened, shifted toward the red end of the spectrum. When it moves toward you, the waves get compressed, shortened, shifted toward the blue. This stretching and squeezing of light by motion is called the Doppler effect, and you have already experienced its cousin in sound. Think of an ambulance racing past you with its siren blaring. As it approaches, the pitch sounds high. As it passes and speeds away, the pitch drops lower. The sound waves are compressed as it comes toward you and stretched as it moves away. Light does exactly the same thing, except instead of a change in pitch, you get a change in colour. So when astronomers spread out the light of a distant galaxy into its full rainbow of colours, they find a kind of barcode printed across it. Certain very specific colours are missing, absorbed by particular elements like hydrogen and calcium in the galaxy's stars, leaving sharp dark lines at precise known positions. These lines are like fixed landmarks. We know exactly what colour they should be when an object is sitting still. And when astronomers look at a distant galaxy, they find those same landmark lines, unmistakably the same pattern but shifted, all of them slid together toward the red end of the spectrum. That shift is called redshift, and it is the fingerprint of recession. The more a galaxy's light is redshifted, the faster it is moving away. This is how Hubble did it. He measured the redshifts of galaxy after galaxy, compared them to their distances, and found a clean, steady relationship. Redshift is the master key to cosmic motion. Every speed I'm about to describe, the Hubble flow and the peculiar velocity alike, is read out of the shifting of these barcode lines in the light of galaxies. Without redshift, none of this would be measurable at all. We would be blind to the motion of the heavens. And notice one more thing, because it matters in a moment. This same effect reveals not just whether a whole galaxy is approaching or receding, but how it spins. One edge of a rotating galaxy is always turning towards you, while the opposite edge turns away. So the light from one side is slightly blue shifted, and the light from the other slightly red shifted. The wider that split, the faster the galaxy is spinning. This expansion-driven motion has a name. Astronomers call it the Hubble flow, after the man who discovered it. And the crucial thing to understand is that the Hubble flow is enormous. For galaxies that are truly far away, the speed of recession caused by cosmic expansion utterly dwarfs any other motion they might have. A galaxy hundreds of millions of light years away might be receding from us at thousands or even tens of thousands of kilometers per second, purely because of the expansion of space. This is the loud, dominant, overwhelming signal in everything we observe. It is the roar of the entire universe stretching. But here is the thing. The Hubble flow tells you almost nothing about local gravity. It is the same smooth, predictable pattern everywhere. If every galaxy were moving only because of cosmic expansion, then the universe would be a perfectly boring place to map, because every galaxy's speed would be perfectly determined by just one thing: its distance. You would learn nothing about where the mass is concentrated. Nothing about which way things are being pulled. Nothing about the hidden landscape of gravity. The expansion is like a vast, uniform wind blowing everything apart at a rate that depends only on how far away it is. And to find structure, to find Laniakea, astronomers needed to see past that wind. They needed to find the second kind of motion, the quiet one, the one that gravity creates. Because galaxies do not only move with the expansion of space, they also move because of the gravitational tug of all the matter around them. A galaxy sitting near a massive cluster will feel that cluster's gravity and drift toward it. A galaxy embedded in a great river of dark matter will be pulled along that flow. This second kind of motion, the motion caused by local gravity rather than by cosmic expansion, is called peculiar velocity. And I want to pause on that word peculiar because it does not mean strange or odd in the everyday sense. It comes from an older meaning of the word, peculiar as in particular, as in belonging to that specific galaxy. The peculiar velocity is the galaxy's own personal motion, the part of its movement that is uniquely its own, the part that is left over after you strip away the universal Hubble flow that every galaxy shares. So here is the full picture. Take any galaxy in the sky, measure how fast it appears to be moving away from us. That total measured speed is actually two things added together. One part is the Hubble flow, the recession caused purely by the expansion of space, which depends only on the galaxy's distance. The other part is the peculiar velocity, the extra motion caused by the gravitational pull of nearby mass. The total speed you observe is simply these two added together. And the entire art of mapping the hidden gravitational landscape of the cosmos comes down to one deceptively simple sounding task. You must subtract the Hubble flow from the total measured speed, and whatever is left over, that remainder, is the peculiar velocity. That leftover motion is the fingerprint of gravity. It is the part that tells you which way the galaxy is truly being pulled. Let me make this concrete with a kind of thought experiment, because the logic of it is beautiful. Suppose you know that a galaxy is exactly 100 million light years away, and suppose that, based on the expansion of the universe, a galaxy at exactly that distance should be receding from us at, let's say, 2,000 kilometers per second. That is what the pure Hubble flow predicts for that distance. Now you go and actually measure the galaxy's speed, and you find that it is receding at only 1,900 kilometers per second. It is moving away from us a little slower than the expansion alone says it should. What does that tell you? It tells you that something is tugging the galaxy toward us, slowing its recession by 100 kilometers per second. That 100 kilometers per second is the peculiar velocity, and it points in our direction. The galaxy is being pulled by gravity towards something on our side of the sky. Or flip it around. Suppose you measure a galaxy at the same distance and find it receding faster than expected, at 2,100 kilometers per second instead of 2,000. Now you know that something on the far side is pulling it away from us, adding an extra 100 kilometers per second to its recession. The peculiar velocity points away from us. By comparing what the expansion predicts against what you actually measure, you can extract that hidden gravitational motion for galaxy after galaxy after galaxy. And once you have it for thousands of galaxies, you can start to see the currents. You can start to see which regions of space are pulling matter toward them and which regions are being drained. And this is enormous. This whole method has a catch, and the catch is the hardest part of the entire enterprise. To subtract the Hubble flow, you need to know how fast the expansion says the galaxy should be moving. And to know that, you need to know the galaxy's distance, accurately and independently. The expansion speed depends entirely on distance. So if you do not know the true distance to a galaxy, you cannot calculate how much of its motion is Hubble flow and therefore you cannot figure out how much is peculiar velocity. The distance is everything, and measuring distances to galaxies tens or hundreds of millions of light years away is, to put it mildly, one of the most fiendishly difficult challenges in all of astronomy. This is the side of the story that does not get told often enough, because it is technical and unglamorous, but it is where the real heroism of this science lives. You cannot simply look at a galaxy and read off its distance. A faint smudge of light could be a small, dim galaxy that is relatively close, or a huge, brilliant galaxy that is enormously far away. From its appearance alone, you often cannot tell. So astronomers had to develop ingenious independent methods to pin down galactic distances without relying on the galaxy's speed. They needed what are called standard rulers or standard candles, objects or relationships whose true properties are known, so that by comparing the true property against the observed one, you can calculate how far away something must be. One of the most powerful tools they developed for exactly this purpose is something called the Tully-Fisher relation. And it is worth understanding because it is precisely the kind of method that made the Laniakea map possible. It is named in part after Brent Tully, the same astronomer who later led the team that mapped our home basin. The Tully-Fisher relation is based on a remarkable connection in spiral galaxies. It turns out that how fast a spiral galaxy rotates is tightly linked to how much total light it actually produces. A galaxy that spins quickly is intrinsically very luminous. A galaxy that spins slowly is intrinsically dim. The faster the spin, the more stars it contains, and the more light it truly pours out into the cosmos. This makes sense when you think about it, because a faster spin means more mass holding the galaxy together against that rotation, and more mass generally means more stars and more light. Now here is why that is so useful. You can measure how fast a galaxy is rotating by studying its light directly, without knowing its distance at all, using exactly that spin shift we saw a moment ago, the blue edge and the red edge, whose split widens with faster rotation. So you measure the rotation, and the Tully-Fisher relation tells you how much light that galaxy is genuinely producing, its true intrinsic brightness. Then, you simply look at how bright the galaxy actually appears in your telescope. A galaxy that is truly very luminous but appears very faint must be very far away, because distance dims light in a precise, predictable way. By comparing the true brightness, which the rotation reveals, against the apparent brightness which you can see, you calculate the distance. And crucially, you have done this without using the galaxy's speed at all. You now have an independent distance, but there is a limitation to the Tully-Fisher relation, and confronting it reveals just how much careful work this kind of mapping demands. Tully-Fisher only works on spiral galaxies, the flat, rotating pinwheel-shaped galaxies like our own Milky Way. It depends entirely on rotation, on that spinning disk of stars, and it is the rotation that the method reads. But not all galaxies are spirals. A great many, especially in the dense hearts of galaxy clusters, are ellipticals, smooth, featureless balls of stars that do not rotate in the same orderly way. Their stars swarm around in tangled, randomized orbits rather than turning together like a record on a turntable. For these galaxies, the Tully-Fisher trick simply does not apply. There is no neat rotation speed to measure. And if you could only measure distances to spirals, you would have enormous blind spots, because so much of the universe's mass is locked up in those elliptical galaxies clustered in the densest, most important regions. exactly the regions whose gravity matters most for the flow. So astronomers developed a second, separate distance tool for the ellipticals, and it is just as clever. It is called the fundamental plane. The idea rests on another tight relationship, this time among three properties of an elliptical galaxy. The first is how spread out the galaxy is, its true physical size. The second is how brightly its surface glows. And the third is how fast its stars are swarming around inside it, which, like rotation in a spiral, can be read straight from the spreading of those barcode lines in its light. It turns out these three properties are locked together in a predictable way. Knowing how fast the stars swarm and how bright the surface glows, you can calculate how large the galaxy truly is. And once you know its true physical size, you compare that to how large it merely appears in your telescope. A galaxy of known true size that appears tiny must be far away, by a precise and calculable amount. Just like that, you have an independent distance to an elliptical galaxy, derived in a completely different way from the spirals, with no reference to its speed at all. Now you hold two independent rulers, Tully-Fisher for the spirals, the fundamental plane for the ellipticals. Between them, you can reach across the whole varied population of galaxies, the rotating disks and the swarming spheres alike, and that breadth is exactly what a reliable map of the flow requires. And that independent distance, however you win it, is the golden key. Because now, finally, you can do the subtraction. You know the galaxy's true distance from the Tully-Fisher relation. From that distance, you calculate exactly how fast the Hubble flow says it should be receding. Then, you compare that to its actual measured recession speed. The difference, the leftover, is the peculiar velocity. The pure, isolated fingerprint of gravity. You have separated the roar of cosmic expansion from the quiet whisper of local gravitational pull. And you have done it for one galaxy. Now you do it again, and again, and again, for thousands upon thousands of galaxies all across the sky, in every direction, near and far. Each one gives you a tiny arrow, a little vector pointing in the direction that galaxy is truly being pulled, with a length showing how strongly. I want you to imagine what astronomers were building as they did this, because it is one of the most beautiful constructions in modern science. Picture a three-dimensional map of our region of the universe, filled with thousands of galaxies, and on each galaxy you place a tiny arrow showing its peculiar velocity, its true gravitational motion, once the expansion has been subtracted away. At first, with just a few arrows, it looks like noise, random little spears pointing this way and that. But as you add more and more galaxies, as the map fills in, a pattern begins to emerge from the chaos. The arrows are not random at all. Over here, across a huge swath of the sky, all the arrows are pointing roughly the same way, like iron filings lining up around a magnet, like grass all bent in the same direction by a steady wind. Vast numbers of galaxies, all streaming together, all flowing towards some common region. And over there, on the other side of an invisible line, the arrows suddenly point a different way, flowing toward a different destination entirely. The currents reveal themselves. The hidden rivers of the cosmos become visible, not as objects, but as patterns of motion. This is the technique that astronomers call reconstruction. They take that field of velocity arrows, the measured peculiar velocities of thousands of galaxies, and they work backwards from the motion to the cause. Because here is the logic. Motion is created by gravity, and gravity is created by mass. So if you can see which way everything is moving, You can mathematically reconstruct where the mass must be that is doing the pulling. It is detective work of the highest order. You never see the culprit directly. You never lay eyes on the great hidden concentrations of dark matter that orchestrate the whole dance, but you see the effect they have on everything around them, the way they bend the motion of thousands of galaxies toward themselves. And from that effect, you deduce the underlying gravitational landscape. You reconstruct the shape of the valley by watching which way the water flows. Think about how powerful that is. Most of the mass in the universe is dark matter, completely invisible, emitting no light of any kind. If you try to map the cosmos by light alone, by counting the galaxies you can see, you would miss the overwhelming majority of what is actually there. The vast dark scaffolding on which the visible galaxies hang. But peculiar velocities do not care whether mass is visible or invisible. Gravity is gravity. A galaxy being pulled by a great clump of dark matter moves exactly the same as a galaxy being pulled by an equal clump of ordinary glowing matter. So when astronomers map the peculiar velocities and reconstruct the gravitational landscape, they are mapping all the mass, the dark and the luminous together. They are seeing the true skeleton of the universe, the real distribution of gravitational pull, in a way that simply counting visible galaxies could never reveal. This is why the velocity flow map is so much deeper than the old density maps. It feels the dark matter. It maps the things you cannot see by watching how they move the things you can. And this brings us back, with new understanding, to that idea of the cosmic watershed I described before. Now you can see exactly how it works in practice. When astronomers laid out their full map of peculiar velocities across our region of the universe, they could trace the flow lines, the streaming paths that galaxies follow as they drift under gravity. And just like rainwater on a landscape, those flow lines naturally divide into separate drainage regions. In one vast region, follow any galaxy's motion and trace it forward, and it flows toward a particular deep gravitational basin. That whole region, every galaxy whose flow lines lead to the same basin, is one structure. It is one watershed. And it is bounded, not by any wall of galaxies, not by any visible edge, but by the dividing line where the flow changes direction, where galaxies stop draining toward our basin and start draining toward the neighboring one. That dividing line is the true boundary. That is the edge of Laniakea. It is a boundary made entirely of motion. To picture the watershed idea one more way, imagine standing high on a mountain ridge during a rainstorm. A raindrop falls on the ground just to your left, and it trickles down the western slope, joining a stream that flows to one ocean. Another raindrop falls just to your right, perhaps only a meter away, and it trickles down the eastern slope, joining a different stream that flows to a completely different ocean. Those two raindrops landed almost in the same place, but they belong to two entirely different watersheds. Because the invisible dividing line, the ridge, runs right between them, their destinies were set not by where they landed, but by which way the land sloped beneath them. The galaxies of the cosmos are exactly like those raindrops. Two galaxies might appear close together in the sky, but if one is on our side of the great gravitational ridge and the other is on the far side, they belong to different basins, flowing toward different cosmic destinations. And the only way to know which is to measure the flow. The density map could never tell you this. Only the velocity map can. Now, I have made this sound cleaner than it really is, and in fairness I should tell you that this work is monstrously difficult and full of uncertainty. Measuring peculiar velocities is one of the noisiest, most error-prone tasks in astronomy. The distances that everything depends on are hard to pin down, and small errors in distance translate into large errors in the calculated peculiar velocity. A galaxy's peculiar velocity might be a few hundred kilometers per second, while its total Hubble recession is many thousands. You are trying to detect a small whisper buried inside a great roar, and to hear that whisper you must know the galaxy's distance with painful precision, because any mistake in the distance leaks straight into your estimate of the whisper. This is why these maps require thousands and thousands of galaxies. No single galaxy's velocity can be trusted very far on its own, but when you average over huge numbers of them, the random errors begin to cancel out, and the real, coherent flows, the genuine streaming of whole regions in a common direction, rise up out of the noise and become unmistakable. The signal of the watershed is written not in any one galaxy, but in the collective motion of many. And so the picture of Laniakea was not handed down from a single brilliant measurement. It was assembled, painstakingly, from a vast catalogue of galaxy distances and velocities, each one wrung out of faint light by clever methods like the Tully-Fisher relation, each one carrying its own uncertainty, all of them woven together by careful mathematics into a reconstruction of the hidden gravitational landscape. The team that did this, led by Tully and his colleagues, gathered the peculiar velocities of thousands of galaxies, subtracted away the universal Hubble flow from every one of them, mapped the leftover gravitational motions into a field of streaming arrows, traced the flow lines through that field, found the watershed boundaries where the flows divide, and in doing so drew for the first time the true outline of the basin we live in. They redefined what a supercluster even is. No longer just a crowd of galaxies, but a region of shared cosmic flow. A watershed of motion defined by where everything is gravitationally falling, rather than by where the lights happen to be brightest. And it is worth naming the actual effort that produced this map, because it did not appear from a single telescope on a single night. It grew out of a long, patient campaign called Cosmic Flows, in which astronomers gathered the distances and motions of tens of thousands of galaxies, edition after edition, each one larger and more refined than the last. The earliest catalogues held a few thousand galaxies. Later editions swelled to tens of thousands. Then beyond 100,000, each galaxy's distance wrung out individually by methods like the Tully-Fisher relation and the fundamental plane, often cross-checked against still other techniques, such as exploding stars of known brightness that serve as cosmic mile markers. Building such a catalogue is the work of many years and many hands. Telescope time begged and scheduled across observatories around the world. Measurement after measurement, error bar after error bar, slowly stacking up into something that could finally be trusted. To feel how delicate this is, imagine you measure a galaxy and get its distance wrong by just 10%. That does not sound like much, but because the Hubble flow you subtract depends directly on that distance, a 10% error in distance can throw off your calculated peculiar velocity by hundreds of kilometers per second, as large as the real signal you were hunting for in the first place. The peculiar velocity is the small difference between two much larger numbers. The speed you measure and the speed the expansion predicts. And small differences between large numbers are exquisitely sensitive to error. This is the razor's edge these astronomers work on, and it is why the sheer number of galaxies matters so much. Any single galaxy's motion is noisy and unreliable, But noise has a wonderful property. It is random. It scatters in all directions with no preference. The true gravitational flow, by contrast, is coherent, pointing consistently the same way across whole regions. So when you average the motions of thousands upon thousands of galaxies, the random errors cancel each other out while the coherent signal reinforces itself and rises clearly out of the murk. The map of Laniakea is, in that sense, a portrait painted not from any single galaxy, but from the collective testimony of 100,000 of them, each casting its small, imperfect vote about which way the heavens are flowing. That is the method. That is how you measure the unmeasurable, how you read the motion of galaxies that no spacecraft will ever reach, how you separate the breadth of the expanding universe from the pull of hidden mountains of dark matter, and how you reconstruct from nothing but the directions things are sliding, the shape of a valley 500 million light years across. It is, I think, one of the purest examples of what the human mind can do when it refuses to be limited by what the eye can see. We could not see the basin. We could only see the light of galaxies and measure how that light was shifted. And from that, by reasoning, by patience, by ingenuity, we drew the map of our cosmic home. But a map of flow lines and watershed boundaries is still, in a way, abstract. It tells you where the currents run, but it does not yet tell you what the basin actually looks like inside, what it is made of, how it is shaped, and exactly where we sit within it. Now that you understand how astronomers found Laniakea by reading the motion of the heavens, the next thing to explore is the structure itself. What does this basin contain? Why is it so strangely shaped, so far from a tidy sphere? What is this thing everyone calls the great attractor that sits near the bottom of the flow? And why is it so badly misunderstood? And where, in all of this immensity, in this branching, flowing, 500 million light-year landscape, does our own small galaxy actually live? Let's step inside and find out. We have learned how astronomers found Laniakea by reading the motion of galaxies, by tracing the flow lines and the watershed boundaries. But a map of currents is one thing. Standing inside the landscape those currents carve is another. What does this enormous region actually contain? How is it built? And where, precisely, does our own small galaxy sit within it? To answer that, I need to walk you up the ladder of structure, from our immediate cosmic doorstep, all the way out to the deep heart of the flow, because understanding where we fit requires understanding the nested set of homes we live inside, each one larger than the last. Start close. Our Milky Way is not a solitary galaxy drifting alone. It has companions, a small huddle of galaxies bound together by gravity that astronomers call the local group. This is our immediate neighborhood, our cosmic block. It contains somewhere around 50 or so galaxies, but do not let that number fool you into picturing 50 grand spirals. The local group is dominated by just 2 large galaxies. One is our own Milky Way, the other is the Andromeda galaxy, which is actually somewhat larger than us, containing perhaps 1 trillion stars to our few hundred billion. There is a third, more modest spiral called Triangulum, and then dozens of small dwarf galaxies, faint little collections of stars that orbit the 2 giants like moths around street lamps. This whole local group spans about 10 million light years. It is held together by its own gravity, genuinely bound, meaning these galaxies will stay together, orbiting one another, for the foreseeable future. In fact, The Milky Way and Andromeda are slowly falling toward each other and will eventually merge billions of years from now into a single larger galaxy. But the local group as a whole, for all its internal drama, is just one tiny passenger in something far greater. Climb up one rung, our local group is being pulled toward, and is part of the outskirt of a much larger concentration of galaxies called the Virgo cluster. This is a genuine cluster, a dense swarm of well over 1,000 galaxies packed into a region roughly 7 or 8 million light years across, sitting about 54 million light years away from us. The Virgo cluster is massive enough that its gravity reaches out across all that distance and tugs on our local group, gently drawing us toward it. The whole sprawling region that includes the Virgo cluster at its heart, along with our local group and many other groups and clusters scattered around it, was historically called the Virgo supercluster, or sometimes the local supercluster. For decades, this was thought to be the largest structure we belong to. Astronomers believed the Virgo supercluster was our home, our final cosmic address, a region about 110 million light years across. And this is exactly where the discovery of Laniakea rewrote everything. Because when astronomers mapped the peculiar velocities, when they traced the actual flow of galaxies rather than just counting where they clumped, they found that the old Virgo supercluster was not a complete structure at all. It was merely one lobe, one appendage, one branch of something vastly larger. The flow lines showed that our entire so-called supercluster, the whole region we thought was our home, was itself flowing, draining, sliding toward a far deeper gravitational basin lying beyond it. The Virgo supercluster turned out to be just a suburb of Laniakea, which is roughly 5 times larger across and contains within it not just our region, but many other former superclusters, all of them revealed by the flow to be part of one connected watershed. What we had thought was the whole turned out to be a fragment. Our cosmic address had to be expanded enormously, and the new, larger home was defined entirely by that shared direction of flow. Now, where is everything flowing toward? This is where we meet one of the most famous and most misunderstood features in all of cosmology. Something with a wonderfully dramatic name: the Great Attractor. You've probably heard the term, and the name itself conjures up a vivid image, doesn't it? It sounds like some colossal object lurking out in the dark, a cosmic monster of gravity, a single titanic thing reaching out to drag galaxies toward it. And I want to correct that image carefully, because the truth is both less sensational and more interesting. And getting it right is essential to understanding our place in Laniakea. The story of the Great Attractor began decades ago, when astronomers measuring the motion of our galaxy and its neighbors found that we, and a great many surrounding galaxies, are all moving in a particular direction at a substantial speed, something like 600 kilometers per second, on top of the universal expansion. Something was pulling a whole swath of the local universe toward one region of the sky. They named the source of this pull the Great Attractor. But here's the catch, and it is a frustrating one. That region of the sky lies almost directly behind the dense, dusty plain of our own Milky Way. When we try to look in that direction, our view is blocked. The thick band of stars, gas, and dust that makes up the disk of our galaxy stands squarely in the way, obscuring whatever lies beyond. Astronomers even have a name for this blind spot. They call it the zone of avoidance, because it is the region of the sky that galaxy surveys have to avoid, since you simply cannot see through the murk of our own galactic plane. It is worth understanding why our own galaxy blinds us this way, because it is a genuinely frustrating accident of where we happen to live. We sit inside the flat disk of the Milky Way, looking at the rest of the universe through that disk. And the disk is not clean glass. It is choked with clouds of gas and fine dust, the soot of dead and dying stars, smeared all around us in a thick band. Visible light, the kind our eyes and ordinary telescopes use, is easily blocked by that dust. The tiny grains scatter and absorb it, so any galaxy sitting behind the band of the Milky Way is simply hidden. Its light soaked up before it can reach us. That is the zone of avoidance, a stripe across the sky, perhaps a fifth of the whole sky, that visible light surveys cannot see into. And by sheer bad luck, the heart of the Great Attractor region lies almost squarely behind it. But dust is not equally good at blocking every kind of light. Light comes in a spectrum far wider than the narrow band our eyes detect, and the longer wavelengths slip through the dust far more easily. Infrared light, which is just light a little redder than we can see, passes through the murk where visible light cannot. Radio waves, with wavelengths longer still, sail through almost untouched. And X-rays, pouring from the hot gas that fills galaxy clusters, can reveal massive structures glowing in a kind of light. The dust does not stop. So astronomers learned to peer through the zone of avoidance, not by looking hard at invisible light, which is hopeless, but by switching to these other kinds of light entirely. Radio surveys mapped hidden galaxies behind the band. X-ray telescopes spotted the glow of obscured clusters. Slowly, in these longer and more penetrating wavelengths, the masses lurking behind our own galaxy's dust came into view, and the Great Attractor region gave up at least some of its secrets. It is a vivid reminder that what we can see depends entirely on what kind of light we choose to look with. So for a long time, the Great Attractor was a genuine mystery. We could feel its pull, measure its effect on our motion, but we could not see clearly what was causing it. But as those penetrating wavelengths gradually pulled back the veil, astronomers peered into the hidden region, and what they found was the crucial revelation. The Great Attractor is not a single object. It is not one monstrous thing. It is a region. It is a broad, sprawling concentration of mass, a gathering of several large galaxy clusters and the dark matter associated with them, spread across a great swath of space. There is a major cluster in that direction called the Norma cluster, and other concentrations of galaxies nearby. And together as a collective, their combined gravity creates the broad pull we had detected. The Great Attractor is better understood as the general direction of, and the broad gravitational focus of, the flow in our part of the cosmos. It is the low region of the landscape, the deep part of the valley toward which the local currents drain. It is a feature of the basin, not a thing sitting at the bottom of it. Calling it the Great Attractor makes it sound like a single villain. It is really more like the lowest part of a valley floor, an area, a zone, toward which water naturally flows because of the overall slope of the land. And here is the distinction I most want to drive home, because it is so easy to conflate these two ideas. The Great Attractor is not the same thing as Laniakea. They are not synonyms. They are not two names for one thing. The Great Attractor is a particular concentration of mass within our basin, the broad focus toward which much of the local flow is directed. Laniakea is the entire watershed, the whole vast region of all the galaxies whose flows lead toward that focus. Think of it this way. If Laniakea is the entire river basin, every slope and tributary and ridge that drains toward a common low point, then the Great Attractor is something like the deep central lowland where much of that draining converges. The basin is the whole landscape. The attractor is a feature within it. One is the container, the other is a region inside the container. Confusing them would be like confusing an entire watershed with a single deepest lake within it. Related, yes. Identical, no. So let me assemble the full nested picture for you. The whole chain of homes. So you can see exactly how it fits together. You live on Earth. Earth orbits the Sun. The Sun is one star in the Milky Way galaxy, sitting out in a quiet spiral arm, far from the galactic center. The Milky Way is one of two large galaxies in the local group, our gravitationally bound cluster of around 50 galaxies. The local group is being drawn toward the Virgo cluster, and together with it and many other groups forms what was once called the Virgo supercluster. And that entire Virgo supercluster is just one branch of Laniakea, the great basin of 100,000 galaxies, all of which are flowing in a broad, average sense toward the deep gravitational region we call the Great Attractor, which is not one object but a sprawling concentration of clusters and dark matter sitting hidden behind the dusty plane of our own galaxy. That is the full address. That is where this letter would be delivered if the cosmos had a postal service. And every single rung of that ladder was discovered by patient human beings looking at light and reasoning their way outward. It also helps to put some real names to the features inside our basin, because Laniakea is not an undifferentiated blob, but a landscape with distinct landmarks. Near its deep central region, in the direction of the Great Attractor, lie rich clusters of galaxies with names like the Centaurus cluster, the Hydra cluster, and the Norma cluster, dense knots where galaxies swarm by the hundreds. Threading out from these are long filaments, named strands of the cosmic web, like the Parvo-Indus filament and others, each a river of galaxies feeding toward the central flow. Our own local group sits within a feature sometimes called the local sheet, a relatively flat arrangement of nearby galaxies, which itself lies out on the far fringes of all this, high up the slope. Even the Virgo cluster, which so dominates our nearest sky and pulls so powerfully on us, sits well off to one side of the basin's deep heart, rather than at its center. The point of naming these is not to memorize them, but to feel that our basin has genuine internal geography, a real arrangement of named clusters and threads and sheets, a topography as specific and as mappable as the mountain ranges and river valleys of a continent, except written across 500 million light years and traced out entirely in the motion of galaxies. Now, I want to address the shape of this thing, because the word supercluster and even the word basin might be misleading you into picturing something far too neat. When you hear basin, you might imagine a smooth bowl, a clean curved depression. When you hear supercluster, you might imagine a great ball of galaxies. Laniakea is nothing like either of those tidy forms. It is wildly, gloriously irregular. It is lumpy and stringy and full of holes. It has no smooth surface, no clean center, no spherical symmetry whatsoever. If you could see it laid out before you, it would look less like a ball and more like a great branching organic thing, a tangle of roots, or a network of rivers seen from far above, or the threads of some enormous cobweb stretched across the dark. Why is it shaped so strangely? The answer lies in how gravity builds structure in the universe, And it is worth understanding because it explains the architecture of everything at the larger scales. In the early universe, matter was spread out almost perfectly smoothly, but not quite. There were tiny variations, regions that were ever so slightly denser than average, and regions that were ever so slightly emptier. Gravity took those tiny seeds and amplified them relentlessly over billions of years. The slightly denser regions pulled in more matter, becoming denser still, while the slightly emptier regions gave up their matter to their neighbours and grew emptier still. But gravity does not pull things into neat spheres on these scales. Instead, matter collapses first along sheets and threads. It drains out of the emptying regions and piles up along filaments, long stringy structures, and where filaments cross, where several of them intersect, the matter piles up most densely of all, forming the great clusters of galaxies, the dense knots in the web. The result is what astronomers call the cosmic web, and it is one of the most beautiful patterns in all of nature. The universe at the largest scales is structured like a vast three-dimensional network. There are dense knots, the clusters, where galaxies crowd together by the hundreds or thousands. Stretching between the knots are filaments, long thread-like rivers of galaxies, sometimes tens of millions of light years long, like cosmic highways connecting the dense cities. There are walls or sheets, broad flattened regions where galaxies spread out across a plane. And surrounding all of this, taking up the overwhelming majority of the volume, are the voids, immense and nearly empty bubbles of space where almost no galaxies exist at all. Regions that can be hundreds of millions of light years across, containing nothing but the occasional lonely galaxy drifting through the dark. And there is a deeper truth hiding underneath everything I have described about the shape of this basin. Something that deserves to be stated plainly, because it is the real skeleton of the whole structure. Everything I have been calling the contents of Laniakea, the clusters and filaments and walls of galaxies, is only the visible part. It is only the small fraction of matter that shines. Beneath it, threaded through all of it, lies a vastly greater mass of dark matter, the invisible substance that gives off no light at all, and that outweighs all the stars and galaxies combined by something like 5 or 6 to 1. The galaxies we see are not the structure itself, they are traces of it, like lights strung along an invisible framework, like dew droplets revealing an otherwise invisible spider's web in the morning, like buoys marking the shape of a current we could not otherwise see. The dark matter is the true architecture. In the early universe, it was the dark matter that first clumped together under gravity because, feeling no pressure from light and gas, it could collapse freely and early, building the filaments and knots of the cosmic web long before the visible galaxies formed. Then, ordinary matter, the gas that would become stars, fell into the gravitational wells the dark matter had already carved, pooling in the densest spots and lighting up as galaxies. So, when you look at the glittering filaments of Laniakea, you are really seeing where the dark matter scaffolding is densest, traced out in starlight. And when astronomers map the flow of galaxies and reconstruct the gravitational landscape that steers them, the landscape they are mapping is, overwhelmingly, the landscape of the dark matter. The basin is shaped by gravity, and most of that gravity comes from mass we cannot see. This is why mapping by motion is so powerful. The galaxies move in response to all the mass, the dark scaffolding included, and so their motion betrays the presence and the shape of the invisible thing that truly defines our home, Laniakea is built from exactly these ingredients. It is not a solid mass of galaxies. It is a particular region of the cosmic web, with its own dense clusters like Virgo, its own filaments threading between them, its own walls and sheets, and its own great voids puncturing it like holes in a sponge. Most of its volume, in fact, is empty void. The galaxies are concentrated along the threads and knots, while vast stretches between them hold almost nothing. This is why the shape is so irregular. It is the shape that gravity naturally carves, following the threads and sheets of the cosmic web, draining the voids and piling matter along the filaments. There is one long, dominant region within Laniakea, where the flow is strongest and the structure most pronounced, almost like the main trunk or central valley of the whole basin, running toward the great attractor region. And our galaxy sits far out along one of the lesser branches, near the edge, near the rim, far from that central trunk. Which brings me to the question you have been waiting for. Where exactly do we live in all of this? And the answer is genuinely humbling. We do not live anywhere near the center. We do not live at the bottom of the basin where everything converges. We do not live in one of the great dense clusters that anchor the structure. Instead, the Milky Way sits way out on the far outskirts of Laniakea, perched up on the high sloping rim of the basin, near the very boundary, near the watershed ridge that separates our basin from the neighboring one. We're about as far from the heart of the flow as you can get, while still belonging to the structure at all. We are not at the center of our supercluster any more than we are at the center of our galaxy or our solar system. We are a frontier galaxy, clinging to the upper edge of the Great Valley, far up the slope from the deep lowland toward which everything drains. There was something almost poetic in that, and also something deeply consistent with everything astronomy has taught us. Every time humanity has asked, are we at the center? The answer has come back, no. Not the center of the cosmos, not the center of the solar system, not the center of the galaxy, and now, not the center of our supercluster either. We live on the edge, on the rim, on the quiet outskirts. And honestly, that quietness may be part of why we are here at all, because the dense central regions of great clusters of violent, crowded places, bathed in radiation and disrupted by frequent gravitational encounters, while the calm outskirts where we sit offer a more stable, gentler environment in which a star like the Sun and a planet like Earth could persist undisturbed for the billions of years that life required. Now, I need to return to something I raised earlier and treat it with real care, because it is the single most common misunderstanding about this whole subject, and it would be easy to come away with the wrong picture when I say that 100,000 galaxies are falling together, falling toward the Great Attractor region. I do not mean that they are all racing inward toward one single point like water swirling down a drain. I do not mean that they are all aimed at one cosmic bullseye where they will eventually collect into a single heap. The reality is far more subtle, far more tangled, and far more interesting than that simple image. Each galaxy in Laniakea is not feeling a single clean pull toward one destination. It is being tugged in many directions at once by many different masses. There is the broad pull towards the Great Attractor region, yes, but there is also the pull of whatever nearby cluster happens to be close. There is the pull along the filament a galaxy is embedded in, drawing it lengthwise down the thread. There is the pull of great hidden concentrations of dark matter scattered throughout the region. And there are pulls from beyond the basin entirely, from even larger masses lying outside Laniakea, which I will come to. All of these competing tugs add up, and the net result is a motion that is complicated, looping, individual to each galaxy. Some galaxies are spiraling, some are being drawn sideways toward a local cluster more strongly than they are being drawn toward the distant attractor. Some follow long curving paths down their filaments. No two galaxies trace the same route, and almost none of them are moving in a straight line toward any single point. The honest way to picture it is, once again, the flowing river, and I want you to hold this image firmly because it dissolves the misconception. Imagine a wide, slow, meandering river and scatter leaves across its entire surface. Now watch. The river as a whole is unmistakably flowing in one direction, carrying everything gently downstream. That is the shared flow, the watershed drift toward the great attractor region. But look closely at any single leaf. It is not traveling in a clean straight line to some destination. It spins. It drifts toward one bank, then the other. It gets caught in a little eddy and circles for a while. It dawdles in a slow patch, then speeds through a narrow one. Its individual path is wandering and complex, shaped by all the little local currents and swirls it passes through. And yet, step back far enough, and the overall motion of all the leaves together is clearly downstream. That is precisely what the galaxies of Laniakea are doing. The basin as a whole flows toward its deep region, but each galaxy follows its own tangled, locally pulled, wandering path within that broad average drift. The flow is real. The shared direction is real. But it is a vast, patient, average tendency, not a frantic collective plunge toward one spot. This distinction matters enormously because it is the difference between a true picture of the cosmos and a cartoon. The cartoon version, 100,000 galaxies all rushing toward a single point, is dramatic but wrong. The true version, 100,000 galaxies each following complex paths, shaped by countless competing gravitational tugs, with a net flow draining toward a broad, deep region, is less tidy but far more accurate, and frankly, far more wondrous. The structure of Laniakea is not the simple geometry of objects falling toward a center. It is the rich, turbulent, organic flow of a whole landscape of matter, responding to the gravity of everything within it and around it. And I want to be equally honest about the numbers and boundaries, because this is a place where precision must not be overstated. That figure of 100,000 galaxies is an approximation, an estimate based on the volume of the basin and the typical density of galaxies within it, not a careful one-by-one census in which someone counted every member. The true number could reasonably be somewhat higher or somewhat lower. Likewise, the size of around 520 million light-years and the enormous mass estimate are best guesses with real uncertainty attached, not exact figures carved in stone. And the boundary itself, the watershed ridge that defines where Laniakea ends, depends on exactly how you choose to measure and define the flow. Draw the flow lines slightly differently, weight the uncertain peculiar velocities slightly differently, and the boundary shifts. Laniakea is not a sharply edged object with a crisp wall around it. It is a vast, fuzzy, flowing region whose edges are defined by something as delicate and as difficult to measure as the average direction galaxies happen to be drifting. This is not a flaw in the science, it is simply the honest nature of what we are measuring. We have found genuine, real structure in the motion of the heavens. but it is structure with soft edges, defined by flow, and we should hold its numbers with appropriate humility. So let me draw the inside of the basin together for you as a single living picture. Picture a vast, irregular landscape spanning 500 million light years, threaded through with the filaments of the cosmic web, studded with dense clusters of galaxies at the crossing points, broadened here and there into great walls and sheets, and riddled throughout with enormous empty voids that make up most of its volume. Through this whole landscape runs a broad, gentle slope, a tendency for everything to drain toward one deep region, the sprawling gravitational lowland we call the Great Attractor, which is not a single object but a collection of clusters and dark matter hidden behind the dust of our own galaxy. Across this entire region, 100,000 galaxies drift like leaves on a slow river, each following its own tangled path under the countless competing pulls of its neighbors, yet all of them, on average, flowing the same way. And far out on the high rim of this basin, near the very edge where the flow begins to give way to a neighboring watershed, on a lesser branch of the web, in a quiet and stable corner away from the crowded violent center, sits one small spiral galaxy, ours, the Milky Way, carrying within it one ordinary star, and one small blue planet, and you. That is the structure of our home, and that is where we live within it. But I have hinted several times now at something beyond, at masses lying outside Laniakea itself, tugging on our whole basin from across even greater gulfs of space. The Great Attractor, it turns out, is not the end of the story of our motion. There is something larger still, farther out, pulling not just us, but the whole attractor region along with it. And once we follow that thread, we have to confront a harder and more profound question. Is Laniakea even a real, permanent thing? Will this basin of 100,000 galaxies hold together, bound forever by gravity? Or is it, like so much else in this accelerating universe, destined to come apart? That is where this story takes its final and most surprising turn. So let's follow that thread outward, beyond the edge of our own basin, because the story of our motion does not end at the Great Attractor. For a while, astronomers thought it might. They had detected that broad pull dragging our whole region toward that hidden lowland, behind the dust of the Milky Way, and it seemed like the Great Attractor region might be the destination, the deepest point, the place where the buck stopped. But when they measured more carefully, when they looked at the motion not just of our local group, but of the Great Attractor region itself, they found something unsettling. The Great Attractor is not sitting still. It too is moving. The whole vast concentration that pulls us is itself being pulled, drawn towards something even larger and even farther away. There is a deeper slope beyond our slope, a greater valley beyond our valley, and the source of that deeper pull has a name. It is called the Shapley supercluster, or the Shapley concentration, and it is one of the most massive structures in our cosmic vicinity. It lies far beyond Laniakea, something like 650 million light years away from us, well outside the boundaries of our home basin. The Shapley supercluster is an enormous gathering of galaxy clusters, far richer and more massive than the Great Attractor region, containing thousands of galaxies clumped together into one of the densest concentrations of matter known in the nearby universe. Its total mass is staggering, on the order of 10,000 trillion times the mass of our Sun, and possibly more. It is so massive that its gravity reaches across that immense gulf of space and tugs not just on individual galaxies, but on the entire Great Attractor region, and therefore on Laniakea as a whole. When astronomers add up the various pulls on our local motion, a substantial fraction of it, perhaps the larger share, traces all the way back to Shapley. The Great Attractor is the nearer, more visible focus of our flow, but Shapley is the more distant, more massive engine lying behind much of it. This is profoundly important for understanding what Laniakea really is and what it is not, because it means our basin is not some self-contained, isolated kingdom sitting alone in space, master of its own destiny. It is embedded in a larger landscape, subject to pulls from beyond its own borders. There are masses outside Laniakea, Shapley chief among them, that influence the motion of everything inside it. Our basin has neighbors, and those neighbors are not passive. They tug at us across the void. And this immediately tells you that Laniakea cannot be the largest structure in the universe, because here is something larger and more massive influencing it from outside. I said this back at the very beginning, and now you can see why it matters so much. We have not found the ultimate container. We have not found the edge of everything. We have found our home basin, one watershed among many, nestled in a still grander landscape that extends far beyond what we have mapped, with structures like Shapley looming beyond our frontier, and very likely even greater concentrations beyond those. Laniakea is vast, but it is a piece of something larger, not the whole. There are, in fact, structures in the universe that dwarf Laniakea in sheer extent. Astronomers have found immense walls and threads of galaxies stretching across distances that make even our 500 million light-year basin seem modest. Sprawling filaments of the cosmic web, spanning 1 billion light-years or more, the largest of them reaching across a substantial fraction of the entire observable universe. So please carry this clearly in your mind. Laniakea is our home, and it is enormous beyond easy comprehension, but it is not the biggest thing there is. It is one feature in a cosmos filled with features, some smaller, some larger, all woven together into the grand tapestry of the cosmic web. Its importance to us is not that it is the largest, but that it is ours. Now we come to the deepest and most surprising question of all, and it is one that turns this entire story on its head. Is Laniakea even a real, lasting thing? Is it a structure that will hold together, bound by gravity into a single permanent object, the way our local group is bound, the way our galaxy is bound? Or is it something more fleeting, more provisional, a pattern in the flow that will not survive the long ages to come? And the answer, which genuinely surprised many people when they first grappled with it, is that Laniakea is almost certainly not gravitationally bound as a single permanent structure. It is not destined to hold together. In the deep future, it will not survive as one entity. Much of it will in fact come apart, drawn away into the expanding dark, never to reassemble. To understand why, I have to bring back the two great forces that govern the fate of everything at these scales, and explain how they wrestle against each other. On one side is gravity, the familiar attractive pull of all the matter in the basin, drawing galaxies together, organizing the flow, building the structure we have spent this whole journey exploring. On the other side is the expansion of the universe, that relentless stretching of space itself that carries galaxies apart, the Hubble flow we learned about earlier. For any structure to be permanently bound, gravity has to win locally. The mutual gravitational pull of the galaxies has to be strong enough to overcome the expansion of space between them, to hold them together against the cosmic stretching that would otherwise carry them away from one another. In a dense cluster like Virgo, or in our tightly knit local group, gravity does win. Those structures are bound. The galaxies within them are held fast and will stay together. The expansion of space does not operate within a bound structure because gravity has locally overpowered it. But Laniakea, taken as a whole, is far too sprawling and far too diffuse for gravity to win across its entire extent. Remember, most of its volume is empty void. Its galaxies are spread across 500 million light-years, concentrated in scattered clusters and filaments, separated by immense gulfs of nearly empty space. Across those enormous distances, the gravitational pull between distant parts of the basin is feeble, far too weak to overcome the expansion of space stretching between them. So while there is a real, measurable flow, a genuine tendency for galaxies to drift toward the Great Attractor region, that flow is not strong enough to bind the whole structure together against the cosmic expansion. The basin is, in a sense, a region of coherent motion superimposed on an underlying expansion that is, across most of its extent, winning. The flow is real, but it is a flow within an expanding space, and over the long run, the expansion will carry most of the basin's distant parts apart faster than the flow can draw them together. And here is the part that makes this truly decisive, the factor that seals the fate of Laniakea, and indeed of all such large structures. The expansion of the universe is not merely continuing, it is accelerating. Sometime in the late 20th century, astronomers discovered to their genuine shock that the expansion of the cosmos is not slowing down under the collective gravity of all its matter, as everyone had expected. Instead, it is speeding up. The galaxies are flying apart faster and faster as time goes on. Something is actively pushing the universe apart, overcoming gravity on the larger scales, and driving the expansion to ever greater rates. We do not know what this something is. We can measure its effects with precision, but its fundamental nature remains one of the deepest unsolved mysteries in all of science. For lack of a better term, astronomers call it dark energy. It appears to be a property of space itself, a kind of pressure built into the vacuum, and as space expands and there is more of it, there is correspondingly more of this dark energy, so its push grows ever more dominant over time. Dark energy is the ultimate fate decider for structures like Laniakea. Because the expansion is accelerating, the distant parts of our basin are not just drifting apart, they are drifting apart at an ever-increasing rate. Over billions and billions of years, this accelerating expansion will steadily win out over the gentle gravitational flow that defines the basin. The currents we mapped, the streaming of galaxies toward the Great Attractor region, will gradually be overwhelmed. The far-flung clusters and filaments of Laniakea, the ones not tightly enough bound to one another, will be carried away from each other by the swelling of space, drifting off into the dark, losing contact, ceasing to be part of any common flow. The basin will be pulled apart, not by any violent event, but by the patient, inexorable, accelerating stretching of the universe itself. What we see today as one connected watershed of 100,000 galaxies will, in the deep future, fragment into separate, isolated pieces, each drifting alone. The great flow that once united them faded into nothing. So I have to correct, very firmly, an idea that might otherwise take root in your mind. Laniakea is not going to collapse together into one giant galaxy. It is not going to merge into a single colossal cluster. The galaxies are not all going to pile up at the Great Attractor and fuse into one enormous object. That is the opposite of what will happen. The bound pieces within the basin, the individual clusters and groups, will each stay bound and may merge internally. Our own local group, for instance, is bound, and the Milky Way and Andromeda within it will indeed merge into a single galaxy billions of years from now. The Virgo cluster will stay bound and hold its thousands of galaxies together. But the basin as a whole, the connections between these separate bound pieces across the vast distances will not hold. Laniakea will not contract into unity. It will be drawn apart into fragments by the accelerating expansion. The structure we have so painstakingly discovered and mapped is, in the grand sweep of cosmic time, a temporary configuration, a passing pattern in the flow, not an eternal monument. We have found our home, and in the same breath we have learned that this home is not permanent, that the ground beneath our cosmic feet is, ever so slowly, dissolving. There is something deeply moving in that, I think. We spent decades learning to read the motion of galaxies, learning to subtract the expansion of the universe from their drift, learning to reconstruct the hidden landscape of gravity, all so that we could finally draw the boundaries of the great basin we live in, and give it a name. And almost in the same moment that we understood what it was, we understood that it would not last. That the very expansion we had to subtract away to find it is the same expansion that will, in the end, tear it apart. The flow that defines Laniakea is a flow swimming against a rising tide, and the tide is winning. Our basin is real, and it is ours, and it is also, on the longest time scales, slipping through our fingers. And I want to return one final time to the matter of humility about what we actually know, because it would be wrong to leave you with the impression that all of this is settled and certain. The figure of 100,000 galaxies is an estimate, not an exact count. No one has tallied the members of Laniakea one by one. The number comes from the volume of the basin combined with the typical density of galaxies, and it could reasonably be somewhat more or somewhat less. The size, that sweeping figure of around 520 million light-years across, carries real uncertainty too, as does the immense mass estimate. And the boundaries themselves, the watershed edges that define where our basin ends and the neighbouring one begins, depend on precisely how you choose to measure and define the flow. Peculiar velocities are difficult to measure, riddled with uncertainty, and reasonable scientists making slightly different choices about how to trace the flow lines will draw the boundary in somewhat different places. Laniakea is not a crisp object with a sharp wall around it. It is a vast, soft-edged, flowing region, defined by something as delicate as the average direction in which galaxies happen to be drifting. The structure is real. The flow is real. But the precise numbers and the exact boundaries are best understood as careful scientific estimates, held with appropriate humility, not as exact and final truths. This is worth dwelling on because it reflects something important about how science actually works and about what kind of knowledge this is. We did not discover Laniakea the way you might discover a coin under a couch cushion, a discrete object simply sitting there waiting to be found. We discovered it as a pattern, a coherence in the motion of thousands of galaxies, revealed only through enormous effort and clever indirect methods, and defined by a choice about how to carve the continuous flow of the cosmos into named regions. That does not make it less real. The flow is genuinely there. The galaxies genuinely stream. The gravitational landscape genuinely has the shape we reconstructed. But the name, the boundary, the precise membership, these are partly a matter of how we choose to describe a universe that does not come pre-divided into neat parcels. The cosmos is a continuous, flowing thing, and Laniakea is the meaningful, well-motivated, but ultimately human-drawn outline of the particular part of that flow we belong to. So let me gather this entire journey together, because we have travelled an enormous distance, both in space and in understanding. We began with you standing perfectly still, feeling nothing, and we discovered that you are in fact being carried through the cosmos at hundreds of kilometers per second, not alone, but as part of a flowing river of 100,000 galaxies spread across 500 million light years, a basin called Laniakea. We learned that this basin was found not by counting where galaxies pile up most densely, but by tracing how they move, by reading the directions of their flow. We learned the method behind that, how astronomers separate the two motions tangled in everything we observe, the universal Hubble flow caused by the expansion of space and the peculiar velocity caused by local gravity, and how, by measuring distances independently through clever tools like the Tully-Fisher relation, they could subtract the expansion away and isolate the gravitational drift. We saw how thousands of those drifts, mapped together, reveal hidden currents, and how the watershed boundaries between those currents, the cosmic ridges where flow divides, define the true edges of our basin. We stepped inside that basin and walked up the ladder of structure from our local group to the Virgo cluster that pulls us, to the old Virgo supercluster that turned out to be merely one branch of the far larger Laniakea. We met the great attractor and corrected its myth, learning that it is not a single monstrous object, but a broad concentration of clusters and dark matter. The deep lowland of our basin, hidden from our direct view behind the dusty plain of our own galaxy in the zone of avoidance. We were careful to distinguish it from Laniakea itself, the attractor being a feature within the basin being the whole watershed around it. We saw why the structure is so irregular, built from the filaments and clusters and walls and voids of the cosmic web, rather than formed into any tidy sphere. We located ourselves honestly, out on the far rim, on a lesser branch, far from the crowded, violent center, in a quiet and stable corner that may be part of why we are here at all. And we dissolved the most tempting misconception, understanding that the 100,000 galaxies are not racing toward one point like water down a drain, but drifting like leaves on a wide, slow river, each following its own tangled path under countless competing pulls, united only in the broad average sense of a common downstream flow. And finally, we followed the flow beyond our own borders to the Shapley supercluster lying far outside Laniakea, pulling on our whole basin from across 650 million light years. Proof that we are not the largest structure, but a piece embedded in something grander. And we confronted the deepest truth of all, that Laniakea is not gravitationally bound as a permanent whole, that the accelerating expansion of the universe driven by the mystery we call dark energy will, over the long ages, overcome the gentle flow and tear much of the basin apart, fragmenting it into isolated pieces, drifting alone into the dark, so that our home, real and vast as it is ultimately a temporary configuration rather than an eternal one. What does all of this mean for you? Standing there, still feeling nothing. I think it means that the oldest question humanity has ever asked, where are we, has just received its deepest answer yet. And the answer's not a place, but emotion. For most of history, we imagined ourselves at a center, the fixed heart around which everything turned. Then, we learned we orbit a star, and the star drifts in a galaxy, and the galaxy belongs to a group, and the group to a basin. And at every step, the center receded, and we found ourselves further out, more peripheral, more humble. And now we have learned the final version of that lesson. We do not live at a center at all. We live on a slope. We live on the gentle sloping rim of a vast cosmic valley, perched near its edge, sliding ever so slowly down toward a deep region we cannot even see directly. Carried along in a flow we only learned to perceive a little over a decade ago. There is no center to stand at. There is only the current and our place within it. And there is something more humbling still, layered on top of that. Not only do we live on a slope rather than at a center, but the slope itself is impermanent. The basin that carries us is dissolving, slowly, across timescales so vast, they dwarf the age of the Earth many times over, drawn apart by the accelerating expansion of space. The ground beneath our cosmic feet is not solid bedrock. It is a flowing, temporary thing, real for now, ours for now, but destined to come apart. We are riding a current that will one day fade, in a basin that will one day fragment, on a slope that will one day flatten into the uniform, expanding dark. And yet, here we are. In this particular moment of cosmic history, in this window of time when the structure still holds, when the flow still streams, when 100,000 galaxies still drift together toward a common deep, we exist. We are conscious. We are able to look out to measure the motion of light that left distant galaxies before complex life crawled onto land, to subtract the breath of the expanding universe from the whisper of gravity, and to draw, however softly its edges, the map of the home we are passing through. That is what I find most extraordinary about all of this. Not that we are small, though we are unimaginably small. Not that we live on the rim rather than the centers, though we do. Not even that our home is temporary, though it is. What astonishes me is that a species of stardust, clinging to a small planet, orbiting an ordinary star, far out on the quiet edge of a flowing basin 500 million light years across, managed to figure all of this out. We could not see the basin. We could only see faint light and shifted colours, and from that, by reason and patience and ingenuity, we reconstructed the hidden landscape of our place in the cosmos and gave it a name from an island language, immeasurable heaven, Laniakea. We learned where we are falling, and we learned that we are falling, and we learned that even the falling will not last forever. And we did it all while standing perfectly still, feeling nothing on a slow current older than the sun, riding the gentle slope of a valley in the dark, looking up,